Hello, my name is Ed Hough. I'm a geologist at the British Geological Survey and I'm the research lead for underground energy storage. And I'll be talking through the presentation, looking at how the ground beneath your feet can support pathways to net zero. So just to put things into context, the natural bedrock beneath our feet is generally very variable, but it does provide many opportunities for the geological storage of energy and waste. So when the bedrock is in suitable composition at suitable depths and thicknesses, bedrock can actually support net zero ambitions. However, we've seen demand for land and the subsurface increase with large deployments for wind farms, both offshore and onshore, for solar power generation. There are different areas under consideration for long-term storage of rad waste, permanent storage of CO2, and also the temporary storage of energy. And because of this demand for land, we think that the effective and considered planning of different deployment of different technologies is required to make the best use of the geological resource. If we look at the map on the right, we can see that this area of the southern North Sea and the different colours illustrate different land uses that might be deployed. So we have areas which have been licensed out for CO2 storage, areas which are licensed for wind farms. We still have a very active oil and gas industry, and on top of this we have areas being considered for rad waste and also temporary storage for energy. So you can see even in this one area there's a big sort of demand on that subsurface space. So just for an overview of the presentation, I'll briefly talk about the role of the British Geological Survey. We'll then look at some of the routes there are to net zero and at some of the properties of the rocks that make them suitable for the temporary and permanent storage of energy and waste. Really, we're thinking of temporary storage of hydrogen, heat, and mechanical energy. We're looking at the permanent storage of CO2. And then I'll illustrate some of the new energy technologies that are emerging using case studies from active research that the BGS is involved in. So firstly, let's look at the role of the British Geological Survey. The British Geological Survey has a national good role in that we undertake public good research into science. We're responsible for providing independent and impartial geoscientific advice. We also provide the National Repository of Data and Knowledge for Geoscientific Information in the UK. We develop services to enable government, business and the public to benefit from the national geological asset. And we also underpin our research with a suite of excellent laboratories and observatory networks. And we develop skills in the geoscience, so we supervise PhDs, for example, and we undertake research and development to try and pursue those aims. And one key area of research that we support is looking at the theme of decarbonisation and net zero, and trying to understand where geology can make a difference. And our work is largely based in the UK. We also have an international presence, and much of our research is applicable internationally. I mentioned net zero on a couple of the slides. So what does net zero mean? So net zero is achieved when the emissions that we remove as a nation are equal to the emissions that we produce. Net negative emissions are where we remove more emissions than we produce. And where sources of emissions are extremely difficult to remove, then net negative technologies are required in some sectors to balance those out. Maybe some technologies, such as some food processing, chemical processes, or transport, where actually achieving net zero may be very, very challenging. So in general, to achieve net zero emissions, we must either reduce activities that produce CO2, be more efficient with the energy that we need and we use, and use low carbon technologies to ensure that the CO2 we do produce is not released to the atmosphere. So just thinking about some of the strategies and policy interventions that there are to help support net zero, the EU aims to be the first climate neutral continent by 2050. And by that, they're looking to try and have a net zero greenhouse gas emissions. Now, this ambition is embedded both at the EU level, but also embedded in strategies for member states. So many member states have individual energy policies, climate plans, and these tend to be very long term, quite ambitious and legally binding. And just to try and drive those strategies together, they are generally looking to improve energy efficiency, looking to decarbonise economies, and looking at driving research and innovation to drive competitiveness. I've seen that energy storage will be important in supporting policy. This brings into question what the best use of the subsurface might be. So having an understanding of capacities, of locations, of also supply and demand for energy is really important in understanding how best the geology can be used and utilised to support those ambitions. Energy can be stored in different ways and released on different timescales, from seconds to months. Longer duration energy storage is more supported really by geology, and this can support the uptake of renewable energy, so wind and solar, and can also supply to balance out variable supply and demand. And geological storage is particularly well suited to longer duration energy storage, but there are still questions on what the optimal use of the subsurface is, and that's where the BGS and other geological survey research comes into play, where we try and understand the potential for geological storage of energy. So let's look at some of the ways that a rock can store energy, or CO2, or in fact air. So rocks can contain natural or engineered void spaces, and these can allow fluids to be stored either in pore spaces, in fractures. Energy can be stored in engineered caverns, which could be bigger, could be stored in mines or in lined caverns. So if you look at the image on the right, you can see in this piece of this magnified image of sandstone, this is about 1 centimetre across, and you can see the pore space there between the natural grains of rock. Pore space in this image is being dyed blue. So it's in that pore space that we would store energy. And energy can be in the form of heat, so heat and cold, can be in the form of pressure, or can be in the form of chemical energy, such as hydrogen or natural gas. So just thinking about storage in porous rocks, these might be depleted oil and gas reservoirs, or they could be rocks that have not held hydrocarbons, so we'll call them saline aquifers. In general, these rocks, we have a fair degree of data describing them, especially for depleted hydrocarbon reservoirs. So we understand the storage volumes, which tend to be quite high. They're quite widespread in distribution. They may have had in the past proven containment for hydrocarbons, so you've got a confidence there for containment. However, there are some questions regarding porous rocks. So, for example, there may be reactions between the energy being stored and any residual hydrocarbons that might be in the rocks. Certainly for things like hydrogen storage, there are questions about cap rocks because the hydrogen has a smaller molecule size, whether or not cap rocks will enable leakage. And there are also questions about microbial action with hydrogen and natural gas storage, which may have a potential impact on permeability and reservoir efficiency. And there's also the potential for any energy that is put into the ground to actually stay in the ground and not be retrieved. So that's what we call residual trapping. So although there are many positives for porous rock storage, there are also a few research questions there that we can take a look at. So in contrast to porous rock storage, there are some rocks which in the underground can be dissolved to create large caverns, large voids. And here we're looking at rocks called evaporites. So we're looking at principally halite. There are other evaporites that can be dissolved in the subsurface to create caverns. In the UK, caverns are typically 30 to 100 meters high and up to about 100 meters in diameter and up to 1,800 meters below the ground. However, elsewhere in the world, caverns up to 800 meters tall and nearly 3 kilometers deep have been developed. So we're talking really big void structures in the subsurface that can store large amounts of energy. Now, caverns have a because of the space, the void space in a cavern, they can allow much more rapid injection and production rates than porous rocks. The evaporites themselves tend to be spatially more restricted, however, which may limit their use. They can store gas at variable pressures, so between near ambient all the way to in excess of 100, 150 bar. They tend to have a lower cushion gas ratio, which can make them slightly cheaper than porous rocks to develop. But in general, they've a fairly limited deployment. Caverns have been developed since the 1970s, but mostly for natural gas. So their deployment for other energy technologies is a big potential, but there are a couple of research questions associated with that as well. So new data is required to improve our confidence in novel energy technologies, and to enable this, the British Geological Survey has developed a network of 3 field sites. We have a site which all these field sites are looking at addressing novel low carbon energy technologies and research questions that are associated with those. We have a site in Cheshire in northwest England, which is looking at aquifer thermal energy storage. We have a site in Glasgow, which is being developed to look specifically at mine water heat. And there is a site in Cardiff in Wales looking at the urban shallow geothermal heat recovery and storage. We also have a series of core scanners at BGS, which we are using to characterize volumes of rock and look at their response to the storage of energy. And we're looking at evaluating the long-term effect of thermal perturbations on aquifers and mines, including the changes in chemistry, microbiology, natural attenuation capacity, and the groundwater flow. So this understanding will help design appropriate regulations and permitting for new energy technologies. So let's take a closer look at our field research site, which is designed to look at aquifer thermal energy storage. So the site is located in the Permo-Triassic Sherwood Sandstone, which is a lateral equivalent to part of the Buntsandstein, which is present under much of northwestern Europe. And really, some of the questions we're interested in are whether or not subtle changes in the bedrock, in the sedimentology, might affect how heat in the subsurface is stored, transported, and released. We're interested in how far heat in the subsurface may travel, and we're also interested in whether or not heat is transmitted between grains as intergranular flow, or the influence of fracture flow on heat transport. And this understanding will help optimize monitoring strategies to understand how heat behaves in Permo-Triassic sandstones. So what does the site actually look like? So we have a video clip here that shows the surface infrastructure of the site. The site itself is about 40 meters by 40 meters, and there are cabling and pumps at surface. But the interesting part for me is the borehole array in the subsurface. So here we have 21 boreholes, each 100 meters in length, and each has a unique set of monitoring capabilities. So from the understanding of the geology, we can develop a series of geological models of heat flow, and we can parameterize these with field data. For example, There is capability at the site for acoustic monitoring, for temperature monitoring, geophysical and geochemical monitoring, and groundwater monitoring as well. And together this gives us the best approximation of heat flow that can be applied and upscaled to large urban areas that may benefit from a much greater deployment of aquathermal energy storage technologies. So the first technology I'll talk about in a bit of detail is called aquathermal energy storage, also known as ATES. And the concept is that during summer, where there may be excess heat, that can then be pumped in the form of hot water into the ground, and where there may be a demand in the summer for cooling, cool water can be extracted from the ground to circulate in air conditioning, and through heat exchangers that can then be used to pick up heat that's then pumped back into the ground. And during winter these schemes are reversed, so where there's a demand in winter for heat, it's the hot water areas in the aquifers can be extracted, used to heat buildings through heat exchangers, and then any cool water is then pumped back into the aquifer. So it's a real circulation of heat and cool. Now there are nearly 3,000 such schemes in the Netherlands, but less than 10 active in the UK at the moment. However, there is a potential to store large amounts, very large amounts of heat and cool, because sandstone reservoirs can be very large volume, very well distributed. So there's a potential there for them to be situated, for schemes such as these to be situated near areas of demand. So there are several big cities in the UK that could benefit from these technologies. They're suitable to support up to sort of district scale schemes, maybe industrial or leisure schemes such as leisure centres, shopping centres, schools, that sort of thing. But there are questions regarding deployment of numerous schemes about how close you can site schemes before you start depleting aquifers, and how close you can have schemes before they start interfering with each other. So I mentioned the low uptake of this technology in the UK, and we're investigating why this might be with colleagues from Imperial College in London and also University of Manchester, to try and answer if there are particular technology reasons or if there's a public perception why the uptake is quite low. So to help us with this, we're looking at understanding where in the UK aquathermal energy storage may be possible, to try and see if there are areas of significant demand that could be supported by geology that can support these technologies. We're also looking at what some of the geological controls on heat storage and leakage may be. So if we look at the slide on the right, we can see this is a cool being pumped into a borehole, and we can start seeing from the ambient flow, the ambient groundwater flow, we can see that the plume of cool is migrating towards the right, towards an abstraction well. We're also looking at impact in these schemes of fractures. So here you can see in the model that we have, where we inject cold water, we can see if we have a couple of fractures modelled, cold water is travelling along those fractures at a much faster rate than it is through the porous rock structure. And this helps us understand and start to model how close together these schemes could be from different users. And we're also looking at the public perception on how stakeholders might perceive such schemes, and how they might understand the benefits of these schemes over sort of traditional fossil fuel sources of heating and cooling. So now let's consider mine water geothermal. So many countries, many regions in Europe have a legacy of coal mining and a legacy of disused mines, and these represent voids which are usually collapsed in the subsurface, generally flooded, which might be suitable for mine water geothermal. So these are associated with many former industrial areas. They can represent at-scale flexible geothermal infrastructures. So if you like, they're a void, an asset in the subsurface that's currently very much underutilized, but does represent an opportunity for a source of hot waters that can be exploited for heat. So we're looking at the BGS has developed a mine site in Glasgow, which is trying to understand the resource that mine water heat could represent. We're also looking at some of the potential environmental impacts of generating flows, groundwater flows in mines. We're looking at developing novel ways of monitoring the perturbations that might be created in the subsurface, and also looking at developing associated technologies that might help us understand the potential for mine water geothermal. So now let's look at CO2 storage. It is an area that BGS has worked on for decades, and recently we've been focusing on the area that's associated with one of the industrial clusters in the UK, located in the northeast of the country, in Teesside and Humberside, and this is located fairly locally to the southern North Sea. So we've been looking at the potential for one of the sandstone reservoirs in the southern North Sea, the Bunter, for a potential CO2 store. And what we've been looking at is how zones, looking at different zones in the Bunter sandstone, and these are areas these are storage complexes that are defined by geological faults and structures, shown on the map on the right. You can see some of the bigger faults and basins there that represent accumulations of Bunter sandstone, and we've undertaken mapping of the actual Bunter itself and the zone boundaries, and we've modelled CO2 storage across this area. So a starting point for these sorts of CO2 storage assessments is generating a geological model, a static geological model. And here you can see an illustration on the slide of where we've looked at considering the Bunter as an open system or as a series of smaller closed systems with boundaries between those different areas. And these models allow us to estimate the areas where CO2 could be stored and the pressures that the CO2 could be stored at. And that influences the volumes and the flow rates that can be stored. And what this tells us is what storage schemes might be viable, helping with planning and licensing areas, and also links to rates of CO2 storage and capture that will be necessary. So in the next few slides we'll have a look at hydrogen, and over the past 5 to 10 years, interest in hydrogen, interest in developing hydrogen economies has become an increasing target for researchers. And if we look at the ambition for the EU and hydrogen, in 2022 hydrogen accounted for less than 2% of Europe's energy consumption. It's been largely used as a chemical feedstock and has been sourced from a carbon-intensive process called reformation of methane, where methane is split. It produces hydrogen but also CO2. Hydrogen has become a priority for the EU to develop, especially renewable hydrogen, which can be produced in a carbon zero way through electrolysis of water. If the electricity is generated from zero carbon technologies such as wind and solar. The ambition for the EU is to produce 10 million tonnes and to import 10 million tonnes by 2030. And the aim is to try and meet up to 10% of EU energy needs by 2050. And one of the quotes from the EU has been that hydrogen stands as a key component in the EU strategy to the energy transition, net zero and sustainable development. And Hydrogen is currently used for chemical products, plastics and fertilizers. In the future, could be a significant energy carrier and actually produce electricity itself. So hydrogen as a molecule is an extremely effective energy carrier. It's got a very high energy storage density when compared with other technologies such as pumped hydro or compressed air energy storage, but it has a very low mass to volume ratio, which means that for the same volume of gas at the same temperatures and pressures, hydrogen would represent around about a third of the energy contained in methane. And this means that the large-scale storage of energy would demand much more storage for hydrogen to provide the same amount of energy as for methane. Hydrogen is already stored at grid scale in solution mine caverns in both the UK and the US, and it has been done for decades. There are questions about whether or not hydrogen can be stored in porous rocks, and there are several demonstrators and facilities under development across the world to look specifically at that. BGS has been looking at one of the research questions associated with hydrogen storage, which is whether or not sandstones would react, porous rocks would react with hydrogen. These reactions may be temperature and pressure dependent and may result in both microbial or geochemical reactions. And we have developed a bespoke experimental technique which is using rock samples, which you can see on the image on the right, and exposing them to hydrogen at elevated temperatures and pressures. We've done this as part of an initiative called the Industrial Decarbonisation Research and Innovation Centre, IDRIC, and there's a link to our research page on the slide just there. So think about whether or not sandstones might react with hydrogen or not. BGS have developed a bespoke laboratory method that exposes rock samples to hydrogen at elevated temperatures and pressures of, we're using currently 50 degrees centigrade and 150 bar, which may be representative of some of the sort of moderate to deeper storage conditions that might be considered for hydrogen storage in porous rocks. We've done this by looking at putting hydrogen itself in a saturated environment and dropping rock samples in pressure vessels. As you can see on the image on the right, hydrogen comes in a valve and out. And what we've done is we've characterized rock samples both before and after exposure to hydrogen and tried to see if there have been any geochemical, microbial or pore structure changes to the rocks. And initial indications are that observed changes to the rock structure, composition and microbial populations are either very minor, or we suspect they may be related to artifacts of the experiment, not due to hydrogen interaction. So the changes we've observed are things such as very minor changes to fines migration, and we've seen minor precipitation of some geochemical components at the pore scale. So as well as looking at the storage of hydrogen in porous rocks, we've also had a program of mapping out where cavern storage of hydrogen could be potentially taken place in the UK, and we've also looked at some other areas across the world. The evaporites in the UK are not present everywhere. They're distributed mostly in the northeast of England, in Teesside and Humberside, down in the south in the Wessex Basin, in Cheshire in the central part of the country, and also out into the East Irish Sea. What we've done to look at the capacity estimates is map out the top and base of halite, and looking at the depth of that halite, we can then estimate how big a cavern could be developed in the halite, and due to the lithostatic pressures, how much the maximum pressures of stored gas could be. And then when we've normalized this per square kilometre, this then gives us a static capacity estimate of how much hydrogen could be stored per cavern per square kilometre. And once we have this information, we can also then look at how fast a cavern could be filled or how fast a cavern could be drained. And that's very interesting then to start thinking about how those caverns could start to support both supply from hydrogen manufacturers and also demand from those off-taking hydrogen. So it starts then to become quite a useful tool to understand how this hydrogen economy could develop in different regions of the UK. And it could also be used to understand how different regions of the UK could actually act as import or export hubs for other regions that don't have the ability for cavern storage. A recent research area that's received a lot of attention over the past 5 years has been the potential for natural hydrogen to be produced from bedrock. So there's understanding that hydrogen can be generated from different geological settings, and we're probably looking at a focus on ultra basic or mafic alkaline rocks. There's a process called serpentinization, which would naturally produce hydrogen, and also hydrogen can be associated with some of the more organic rich rocks such as coal. However, migration and trapping, generation, migration and trapping mechanisms are poorly understood. The identification of commercial quantities of hydrogen is difficult. Exploration and monitoring strategies are not well established. Baseline studies are in general very poorly understood. However, there have been some very early promising results, notably as a site in Mali. There are also sites of interest in Spain, Australia and parts of the US that are receiving a lot of attention at the moment. Let's move on to another energy technology, in fact the final energy technology I'll talk about, which is called compressed air energy storage, or CASE. So this is a technology that can use wind and solar energy power to compress air through turbines and compress air into storage caverns developed again in evaporite rocks, or there's a possibility that porous rocks could be used to store compressed air. So this is mechanical energy. If you remember from physics, when air is compressed, it heats up, and that heat of compression can be stored or it can be vented to atmosphere. If the air is compressed and the heat is stored, then when the air is released to drive turbines, that stored heat can be then used to heat the air back up, so you don't get problems with condensation and freezing of turbines. If heat is not stored and is actually vented in the compression phase, then the air, once it's released, must be heated up then using fossil fuels. So we're looking at options now for using low carbon energy or heat storage to heat that, either store the heat of compression or heat the air up on release. If if technologies can be developed to have that heat which is low carbon or zero carbon, then compressed air energy storage could be a true zero carbon technology in some scenarios. So it has a huge amount of potential. So some of the research questions that the BGS are looking at with partners at Birmingham University, Leicester University and Nottingham University are looking at trying to optimize system design, so looking at improving the round-trip efficiency, looking at the techno-economic assessments, looking at thermal management strategies, so can heat of compression be stored at different enthalpies, so can we store very hot heat, can we store cooler heat, and then can that be used then to heat up air on release. We're also looking at some of the potential environmental impacts and looking at where higher pressure compressed air energy storage might be viable, and some of the geological controls there might be on that. So as part of our work looking at the potential for compressed air energy storage, we've mapped out where we think caverns can be developed and the operating pressures that they can operate under, using a modified approach that I described for the hydrogen storage. So again, we can look at mapping out top and base of halides. We can look at the depth of those halides and estimate the maximum operating pressures that can be sustained in storage caverns. And again, we can start looking at daily injection and production rates from those different areas. So for example, this map from the Wessex area, which is in Dorset in the southern part of England, indicates that it's only in the central part of the basin, of the salt basin, that salt is deep enough and thick enough to sustain storage pressures above about 350 bar. Again, we can look at how much exergy, so that's the energy that the compressed air could actually result in. We can look at the amount of exergy per cavern per square kilometre, and again that feeds into understanding where how much energy could be stored, and then we can have a think about whether or not energy is best stored, optimally stored, as methane or hydrogen, or as exergy and compressed air energy. So in summary, there are a wide range of natural geological storage resources, not just restricted to the UK. I know the examples I've used are from the UK, but there are similar rocks across different parts of Europe. The variety of bedrock types, whether of suitable composition, depth and thickness, can support progress to net zero by supporting technologies such as heat storage, compressed air energy storage, hydrogen storage, permanent storage of CO2. However, the subsurface can quickly become very busy, especially when you consider the demands of land and of seafloor from wind farms, from rad waste demands, and for that reason the effective planning and subsurface use needs to be carefully considered, and one of the inputs to that understanding is understanding the geological resource. So thanks for listening. I'd just like to thank different research teams that have supported some of the case studies that I've worked on. So from aquifer thermal energy storage, looking at heat storage, looking at compressed air energy storage, the IDRIC research teams. We have a project looking at the offshore energy transition and the use of the North Sea, Southern North Sea in the UK. Also colleagues at UK GEOS, and also from the IEA TCP Task 42. And special thanks to the colleagues listed at the bottom of the slide there. So thanks for listening. And yeah, if you have any questions, please don't hesitate to get in touch, and do take a look at the current research from the British Geological Survey on the website on the slide just there. So thanks again.